All right, guys, welcome back. Let's begin with a reminder about the final. May 17, 9 to 11 a.m., same location as the class. I hope works out for everybody. So the final is, the time and date is set by the university, and nothing I can do about it. It's made so that doesn't have conflicts with everybody else's classes. Okay. All right. So the last we've got 4 lectures left, I think, and so the final topic that I want to describe to you is the idea of control. And how do we control things that we build models for? So, we've been talking about models that say you have some state, that state changes based on some input that you give to it, and there's some noise that affects it, and there's some measurement that you make that depends on that state, and there's some noise on it too. And the objective is to figure out what is the input that you should give to the system. So the problem of control is figuring out how do you make that system do what you want it to do. And this is the final topic that I want to show you. And the basic important idea that we're going to get to is the concept of a Bellman equation, which is a description of how do you do something now based on a future goal. And so the foundation of things like dynamic programming is this idea that you have a long-term goal. You want to win the game, you want to live a happy life, you want to retire in Bahamas, that kind of thing. And now the question is, well, okay, you're in Reza's class today. What should you do now in order to achieve your long-term goal? Is this even the right thing to do? Should you take this class, given that you want to retire in Bahamas? Perhaps not. That's the kind of answer that we want to be able to get. And so if we had the proper model of how the inputs that you provide to the system provide changes in your outputs and the measurement that you make, then the question is, what is the action that you should do in order to achieve some long-term goal? And so, almost all the class that we've been discussing is about learning models. From prediction error, right? So you have some model that says, here's what I think is going to happen, here's what actually happened, and the difference between these guys is my error. And this is what I'm going to use to update my model. But having an accurate model is useless unless you can do something with it, which means you can control something. And so today, and for the next couple of lectures, our question is about how do we control that system, assuming that we have the right model. And the material that we're going to learn have to do with the concept of having a notion of, well, how do we determine the goodness of what is it that you want to do? So there's something you want to achieve, and we have to describe a metric of how good is the action that you got compared to what you want. So, for example, you might throw a ball, and there's a hoop, and if it goes inside the hoop, you get something for it. If it goes outside the hoop, you don't get anything for it. So it doesn't matter if it goes close to the hoop or really far from the hoop, it's the same miss. If it goes in the hoop, you get something. That's one kind of a reward function. Another kind of reward function is when you're playing horseshoe. When you're playing horseshoe, you throw the horseshoe, and the closer it is to the pin, the better it is. That's a different kind of a reward function. Then there's the effort component of the task, meaning that, well, how much does it cost you to do that action? And that effort with the reward together becomes what's called a utility, which is describing the goodness of your performance. And based on that utility, we will find how to set the command, U. So there's some utility associated with your behavior. the thing that you measure, y. And then what we want to know is that, how do we find best u action so that what we did, y, maximizes some j of y and u, where this is the utility of the action. So, your actions that you did might have a result, y, that give you some reward. You do retire in Bahamas. That's great. But then you had to do some actions to get there. Those were the commands that you generated. Those are the behaviors that you did. And optimizing this utility is the basic problem in control. So we're going to give some examples of how to do this. And as we do it, we'll build up our tools, and we'll eventually get to the Bellman equation, which is the basis of dynamic programming. Okay, so pretty grand, right? We're going to solve some pretty amazing things. I often think that if you knew how to do this and you had computers that were fast enough, you would just determine your life. You would say, this is how I'm going to behave. Yeah.
Is it important how we get there, or is it just important that where we find
No, it's important how you get there. Absolutely, because you will see that your utility depends not just on the final point, but the path you took, in the sense that you had to spend effort to get to Bahamas, right? You had to go to school, you had to go get a job, you had to get married, all of these actions, and then you retire. So all those things are going to accumulate, and at the end we're going to compare you to somebody else and say which one was better. And some people may not end up in Bahamas. Some may end up in Cancun, which is not close to Bahamas, but it's also not bad. So all of these, are concerns for our cost function utility. And we're going to get to describing how to do it. It's exciting, right? I mean, mathematics, you can do these things with it. I think it's like, gosh, you can see the future where mathematics is going, determining behavior. When you're born, here's your utility, here's the actions from now on. If the world wasn't stochastic, perhaps that would be the right thing to do. But at least we'll have a control policy. All right. So these ideas really first arose in at least in the way I think about it, in robotics. And let me describe to you what people in robotics were thinking about. So people in robotics, they had a machine that they wanted to go along some path. So let's say it's a robot that's going to be welding something. So there's some goal that it needs to achieve during some time. So I'll put a Y here to be consistent. So what that means is that the robot has to move this weld along some path, and this path is described in time. So you might have a cost, the utility, that looks something like this. T is equal to 1 to n of y of t minus yg of t squared plus u of t squared. So this would be your reward, in a sense, which is how close you are to the goal trajectory. And this would be your effort. How much commands your motors had to expend, how much forces they had to produce in order for you to do that. And of course, this is a scalar, right? So J is just a scalar. It gives you a number for the action that you did. And so in principle, it solves problems that have no one-to-one relationship between the, what is it the output it needs to be and how did you get there. So for example, you can have a trajectory, you can have another trajectory. Each of them gets a number. And the one with the best utility is the best action that would be performed. So do you have any questions about this so far? So you notice that in this formulation, the entire trajectory is described, right? So the robot is told, this is the trajectory to move. Now, in general, you don't know the trajectory. You just know where you want to be. So in our question with regard to, throwing a basket at a ball, you just, throwing a ball at a basket. You just know that the ball should go in the basket. You don't know the trajectory for the ball for it to go. So that, in principle, you don't know the trajectory. You just know that at the end, that's what you want. But we can begin with what robotics did, which is to have a trajectory for the robot to move. And you can see that was because that they wanted machines that would weld and things like that, where the trajectory is well specified. But the important problem that we're going to be able to solve with this approach is one where we're going to get a unique solution when there is many ways to do something. So I'm going to give you an example from your own body. So suppose that we ask you to take a bar and hold it between your hands. Hold it like that, and then put forces on it. And so I forgot to mention, so I'm covering, so the material that I'm covering is chapter 10. And your homework is going to be very similar to this example that I'm giving you right now. So suppose that I ask you to hold a bar, and then this bar has got a force transducer on it, and I ask you to produce a force. So push upward, push left, push right, push down, so forth. So you produce some vector of force, like that, in 2D. And of course you have muscles that are activated, and so you have various muscles. So I'm going to draw for you what we call pulling direction of each wrist muscle. So maybe you have 8 muscles in your wrist, and some muscle, when it activates, it pulls in this direction. We're going to call that P1. And another muscle, when it activates, it produces a force in that direction called P2, and whatever. Some distribution of muscles. So each of them is the direction of force that it pulls when that muscle gets activated. And so the force that's produced by muscle I, force vector, is some scalar ui times some vector pi. So these are the vectors. This is the scalar. So that muscle, when it gets activated, pulls in that direction. And you have 8 muscles in your wrist. So what I want to know is that when I tell you to produce this force, how do you distribute the activity to the various muscles so you can produce this force that I asked you to do? So it's a redundant scenario, right? How do you divide up this cost, produce this force among the various muscles? And so let's write this problem mathematically. Let's see how we solve. Do you have any questions about this before I start? You see what the problem is? So you have 8 muscles, each pull in various directions, and when you activate them, you're going to get a sum of those vectors. And so how do you sum them up to produce a particular force that you need? So we're going to have a vector u that is going to be all the individuals' muscles, the activity. So I don't know, we have 8 muscles. And I'm going to have a matrix P that's going to be P1, P2, P8. Each one of these is this column vector. So this is a 2 by 8. This is an 8 by 1. And then the force that you generate is a matrix P times vector U. So that's it. You get a 2 by 1. So this is the total force produced by all muscles. So your task is to produce some goal force, Fg. So that's our goal force. So we have a utility or a cost. That cost is J. Fg minus Pu transpose Fg minus Pu. So I'm going to have a quadratic cost associated with matching the goal force, and I'm also going to add something that is going to penalize how each muscle was active. So total sum of activity I'm going to penalize, and this numerator, sorry, this exponent is going to be something that I'm going to be interested in. So we're going to consider m when it's equal to 2 and m where it's almost 1. So I want to show you what the difference is when there is this penalty associated with the motor commands. So our goal is match this force while being essentially as frugal as possible in the motor commands that you generate. So let's begin with m is equal to 2. So we're going to penalize the motor commands as a quadratic function. So in that case, then J is equal to Fg transpose Fg minus 2 times Fg transpose Pu plus U transpose P transpose Pu plus lambda U transpose U. So we want to find the optimum command, dj du. It's going to be equal to minus 2 times P transpose Fg times U. So dj du has to be an 8 by 1. So this is P transpose is going to be an 8 by 2. Fg is a 2 by 1. U is, sorry, transpose. No. It's not transpose. There is no U here. Yeah, I don't know how to take derivatives. Okay. Plus 2 times P transpose Pu plus 2 times lambda U. Okay. All right. Whew. Feel better. All right. So this is okay. This is okay. 2 times lambda U. This is all the right size. It's an 8 by 1. Every one of our multiplications is an 8 by 1. So we set that is equal to 0. Solve for U. U is going to be equal to P transpose P plus lambda minus 1 times P transpose Fg. Okay, so this is when m is equal to 2. So when I'm penalizing my motor commands by an exponent that squares it, this is the optimum distribution of the commands to the various muscles that both get me to match the target force and minimize the sum of the squared activity in the various muscles. So what does this mean? So let me draw for you our solution. So our goal was to say here's some goal force that you have to produce, and the question is, what is the command that I should send to each of the muscles? So let's pick one of the muscles. Suppose that the muscle that I'm interested in has a pulling force in that direction. And so this tells us that, well, for each force that you want, I can tell you how that muscle that you're interested in is going to get activated. So you know, if I want to force in this direction, I'm going to have some activity, a little bit more, a little bit more, a little bit more. Basically, you're going to get what's called a tuning function. It'll look like this. It says force in each direction has a particular amount of activity associated with that muscle. So this is when m is equal to 2. if you now solve the same problem for m that's approximately equal to 1, something less, what you're going to get is that that same solution is going to be, it's going to look like this. Narrower. So this means if you penalize activity in this muscle, it'll share more, meaning that it will be activated less in its preferred direction and more in other directions. Whereas if you make it so that I don't penalize activity very much, then you're going to get something that's going to become essentially winner take all. So the idea is that you can measure this in the actual nervous system. You can see what is the amount of activity in the muscle, and you can ask, what's the cost function that's being used? Is it something that says activity is really costly, we should, penalize it a lot, in which case you're going to get a broad tuning function? Or is it the case that activity doesn't cost me very much, and I could activate this muscle as much as I want, in which case you're going to get a narrow tuning function. So let me stop for a second, see if you have any questions. Yeah?
When we are optimizing with that penalty term, does it mean that we are optimizing subject to the norm of when m is equal to the norm of u equal to 0? Because that term is like the Lagrangian multiplier.
Right. We're going to get to the Lagrangian multiplier. So lambda tells you how much weight we're going to have for this versus this. But when we solved it, we have to have lambda known. So we didn't solve for lambda. We just assumed lambda.
No, that means that we are optimizing the first term subject to sigma of u I to power of 2 equal to 0.
No. So that's not the cost function. So we're not using it as a Lagrange multiplier. I will get to the Lagrange multiplier. All I'm saying is that there is some cost associated with accuracy and some cost associated with effort. That's all. The question you ask we'll get to in just a few minutes. The concept of a constraint minimization. Okay, so the whole point about this was to tell you that you can assume some cost function, and then you can say, okay, how should the system distribute the activity to the various muscles? And here's how it should distribute it if m is equal to 2 and lambda is some number. And here's if you should do it if m is equal to 1. And so you can ask, okay, well, if you actually look at the system, how does it do it? And then that gives you a sense of, one versus the other. But the deeper point that I want you to know is that if you're going to penalize things heavily, then the elements in your system will share the load. Whereas if the penalty is small, then they're going to be more like winner take all. One or two elements will take all the load and everybody else will be silent. Okay. All right. So now let's do a little bit more sophisticated type of analysis. Let's add some stochasticity into our system. So noise. And see how that affects our cost function and how to optimize it. So let's do the same problem again with our muscle. Would now say that the force that they produce depends on the input that we gave them and their direction of action, PI. But then these are going to be noisy things. So I'm going to have it times 1 plus Ki phi, where phi is a random variable with mean 0 and variance 1. So K is some constant. So what this means is that the force that's being produced will scale with the input U, but then this noise is also going to influence the force. And as the input U increases, because the noise is being multiplied by U, then the noise in the force also increases. So this is called signal-dependent noise. And many biological systems are like this. So what does that mean? So if you have some low level of force, it looks like this. But if you increase the force, it looks like this. So the noise grows. Okay. So I want to show you how do you solve these class of problems when you have stochasticity. And so we're going to be considering this. So we have f of I. So the expected value of f of I is u of I times p of I, right? Because the expected value of this equation is the only noise term is here, and its mean is 0. So the expected value is just the left side. What about the variance of f of I? Well, that's u is a scalar, so ui becomes a squared. P is a vector, pi transpose, and then ki is a scalar, ki squared. So that's a variance of f of I. All right, so my utility, J, is fg minus f transpose fg minus f plus lambda ui to the mth power, where f is just the sum of the individual forces fi, which is the sum of ui pi 1 plus ki phi. So the expected value of f is just this sum of ui pi, which is matrix P times u. Then the expected value of the utility function is the expected value of, I'm just going to multiply it through, ft f minus 2 times f transpose fg plus f transpose f plus lambda sum of ui raised to the power m. Okay, so I want to, because j is this is a stochastic now variable, so what I want to do is find the command u that minimizes this expected value of j. And so to do that, I need to find the expected value of this terms, so that you need to find the expected value of this term, expected value of this term, and expected value of this term. Well, expected value of this term is just itself because fg is a constant. Expected value of this term is just expected value of fg. But then the question is, expected value of f. But the question is, what's the expected value of this, f transpose f? Because this is a squared variable. So you have a variable that has noise in it, and you're going to square it. So when you take that and you square that variable, the question is, what's the expected value of that squared variable? Well, if you think about it, it should be the expected value of the mean of the variable, so the mean of the variable squared, but then the noise gets squared as well. It gets added on top of it. So we will need to have, in order to square a random variable and find its mean, we need to know the mean of the random variable plus the variance of that random variable, because that's going to become the new mean of the squared variable. So that's what I'm going to do. I'm going to derive it for you. In this case, for a vector. So we want to know what's the expected value of f transpose f. This is obviously a scalar, where f is our vector. Okay, so let's begin with variance of f. Well, from our definition of what variance is, that's f minus expected value of f times f minus expected value of f transpose, which is expected value of f transpose minus expected value of f expected value of f transpose. So that's the definition of variance. So from this, we can say, well, the expected value of f transpose then is going to be variance of f minus thank you. Okay, well that's close, but it doesn't give us this, right? We want f transpose f. We don't want f transpose. So how do we get it to this? Well, that is equal to the expected value of f transpose f. That's equal to the expected value of the trace of f transpose. So the trace of f transpose is f transpose f. But trace is a linear operator, so I can take it out. So that is equal to the trace of this expected value, which is this. So that becomes the trace of the variance of f plus the trace of the expected value of f, expected value of f transpose, which is equal to the trace of the variance of f plus the trace of this is just expected value of f transpose expected value of f. Okay, so now we have this expected value. All right, so now our function is this. We have to find this expected value. So the expected value of our utility, our cost, is the goal force squared minus 2 times expected value of f transpose, fg, plus the trace of the variance of f, plus the expected value of f transpose, expected value of f, plus lambda sum of ui raised to the power m. So this term here, the trace of the variance of f, is just the sum of the variance of f, the individual variances, which is ui squared ki squared pi transpose. Which can be written as P K U transpose P K U. And then this term is U transpose P U. Expected value of f is just p times u. So that's that. So we get a quadratic function, you know, in terms of u. This term here has a u in it. This term, it has a u in it. This term has a u in it. So what we see is that for a system with signal-dependent noise, the expected value of the utility has a penalty term u transpose u in it. So regardless of this term, this variance term has u transpose u in it already, as you can see here. So if you have a system that has signal-dependent noise, in order to meet a goal, you are naturally penalizing, using a quadratic function, the commands that you're sending. And so what we just did is to say, if your cost is based on stochastic elements that have noise, and that noise depends on the command u that you send, then the expected value of that noise, the expected value of the utility will depend on u. And so in this case, because signal-dependent noise was dependent on u squared, the variance here would depend on u squared, effectively you are penalizing the commands u independent of whatever you may be penalizing there. All right, let me stop to see if that made some sense. If you have any questions about it. Yeah.
What's the dimension of K?
Big K? Yeah, it would just have to be, you would need to write this sum in terms of something that, so P is a 2 by 8, U is an 8 by 1, so K is an 8 by 8. I think it's a diagonal matrix with the KI's down the middle. Okay. All right, let's do an experiment now. Let's use some of this to do an experiment. Suppose that you have a little force transducer, and you have somebody come with their fingers, put the index finger there, and then put the other index finger here. And you tell them to produce a force so that the sum is equal to some goal force. Okay? So the question is, how will they divide it up between their left and the right hand? Let's do that. Let's do the math so we can figure it out. So the force by their left hand is going to be normally distributed with some mean UL and some variance KL squared UL squared. So they're going to produce noisy forces with their hand, and the mean of that is going to be based on some command U that they're going to push on it, and the variance of it is going to grow with the command U. Similarly for the force on the right hand. And so, you know, you can measure this, right? So you can have them put their finger on just one finger and tell them produce some force U sub r, and then when they do that, you say, okay, what's the variance in that force that they're producing? You can measure this variance, and you can do the same for the left hand, and you can measure this variance, right? Okay, so now you say do it together. So that now you have a cost, J, that says, all right, force in your left hand plus force in your right hand minus some goal force, G, squared. So you want to be as close as possible to this goal force, but we're going to penalize you the farther away you are from it. Okay, so now let's solve our, I won't penalize the commands individually because we're already going to have a penalty for them here in the cost function, as you will see. So, okay, we want to know the expected value of J. because what we want to know is that u that UR and UL that minimizes the expected value of J. Okay, so what's the expected value of F squared? Some force. Well, whether it's FL or, so let's say FL. The expected value of FL squared, because we're going to have FL squared here and FR squared here. So what's the expected value of FL squared? That's the expected value of FL squared plus the trace of variance of FL, if FL is a vector. If FL is a scalar, which is in our case, then expected value of FL is just the expected value of FL squared plus what? Just the variance of FL, because that's just a scalar by itself. All right. So expected value of our utility J. That's going to be the expected value of FL plus FR minus G quantity squared plus the variance of FL plus FR minus G. That's equal to UL plus UR minus G squared plus the variance of FL is KL squared UL squared. Variance of FR is KR squared UR squared. And variance of G is 0. So, all right, now find the command UL that minimizes our utility. So we find the derivative of J with respect to UL. Plus 2 times KL squared UL. So I get UL is equal to G minus UR divided by 1 plus KL squared. Similarly, one can solve for UR. But the important thing I want you to notice is that UL depends on KL, which means that as noise, KL increases, UL decreases. Okay, that's an interesting concept because it's saying that if you're right-handed, so what does it mean when you're right-handed? What that means is, it doesn't mean that you're going to produce more force. If I had you grip something with say you're right-handed, with your right hand and tell you to produce the maximum force you can, you're not stronger with your right hand than your left hand. But what you are is that if you're right-handed, you have lower noise in your right hand than your left hand. So our result here says that if you have more noise in your left hand, you will produce less force with your left hand. So you will divide up the problem based on how well you can control each muscle. If you have a muscle that you can't control very well, you will penalize it. You will give it only small commands. If you have another muscle that you can control very well, control meaning low noise, then you will give it more effort. So you will distribute effort. If the objective is to meet a goal, J, produce this goal force, and you're going to get penalized by being far or below this goal force, then what you want to do is to give as much input to the effectors, the elements that have low noise. And that's what the solution to our problem is. Do you have any questions about that? All right. Okay, final topic. So we had an earlier question about Lagrange multipliers, and Ketchen gave you a intro to Lagrange multipliers. I just want to review it for you because Renee also did. Okay. Because it's a concept that plays a central role in the notion of a cost function and how we minimize cost functions. So, having a constraint. So let's give you an example. So suppose you have a point here, and let's call this point x0, y0. And you want to be as close to this point as possible, but you want to be on this line. So find a point xy that is, or x star, y star, that is as close as possible to x0, y0, but lies on the line y is equal to mx plus b. So we have a cost j, so that the farther away we are from x0 and y0, the worse it is. That's our cost. Subject to the constraint that y minus mx plus b is equal to 0. So we have a j as a function of x and y, and we have a constraint as a function of x and y, where g of x and y is y minus mx plus b. So we would like y minus mx plus b to be 0 while we're minimizing our cost j. So let's solve this problem. Okay, so the idea is to set it up as follows. So what's dj d vector x, where x vector is xy. dj dx. All right, we're going to find the derivative of this with respect to x and y. That's going to be 2 times, derivative with respect to x is 2 times x minus x0. Derivative with respect to y is 2 times y minus y0. All right, so then what's the derivative of g with respect to x? That's derivative of g with respect to x is minus m, derivative of g with respect to y is 1. That's what that is. So what we're going to do is we're going to write this augmented function a, j. It's going to be some function of j of x and y plus now something that we call a Lagrange multiplier times g of x and y. And what we're going to do is we're going to find a scenario where dga dx is equal to 0 and dj d lambda is equal to 0. And of course, if that's true, that's g of x, right? So g of x and y. So if we can, sorry, dja. If we can find a scenario where both of these equations are true, dja, this augmented cost with respect to x is equal to 0, and dja with respect to lambda is equal to 0, what that means is that, well, if this is true, if dja d lambda is equal to 0, which means this term must be 0. G of x and y must be 0. So then we've met the constraint. And if that's true, then when we minimize dja dx, we're really minimizing dj dx, which is what we wanted to do. So here's what we did. We had a cost. We had a constraint. We put them together using a multiplier. And then we said, we have to now, we don't know what this multiplier is. But what we say is that, well, these are the two constraints that you have to meet. The derivative with respect to x has to be 0, the variable that you're looking for, and the derivative with respect to lambda has to be 0. If the derivative with respect to lambda is 0, then you've met the constraint. Then you found an x and y that indeed brought this g to 0. So that means you're on the line. If you did this, dj dx was equal to 0, and this was 0, this means that you actually minimized j. Okay, so for our problem here, all right, so what's derivative of ja with respect to the vector x? That's dj with respect to the vector x plus lambda plus lambda times derivative of g with respect to x, which is equal to 2 times x minus x0, 2 times y minus y0, plus lambda times minus m and 1. That has to be equal to 0. And then our second equation is derivative of ja with respect to lambda has to be 0. That's equal to g of x, which is equal to y minus mx minus b. That has to be equal to 0. So look, we have 3 equations, 3 unknowns. Here's one equation, here's a second equation, here's a third equation. What are our unknowns? So 3 equations, 3 unknowns. X, y, and lambda. Those are my 3 unknowns. Okay? All right. All right, so let's use this. Let's use this to solve a problem. So we have 8 muscles produce force to match a goal. So our cost, J, is U transpose U. So we're going to square our cost, our commands, and that's going to be my cost. My constraint is that PU minus FG has to be equal to 0. So the force that I produce minus the goal force, that has to match the goal force. So I have to produce this goal force while minimizing the squared cost. Okay, so how do I do it? I set up an augmented cost to sum of the 2 things, U transpose U plus lambda transpose P times U plus FG. Okay, so U is an 8 by 1 vector. P is a 2 by 8. U is an 8 by 1. So I have to produce a 2 by 1 vector to match my goal. 2 by 1, right? So this is a 2 by 1 constraint. So this is lambda is a 2 by 1. So I'm going to have two Lagrange multipliers here because this is a vector. In order to make it a scalar, I multiply it by the transpose of the lambda, and then here's my the cost. So just to be clear, I have a vector associated with my Lagrange multiplier. There are two Lagrange multipliers here, one for each component of the force that I have to produce. All right, so now what I do is that I find the derivative with respect to u. That's equal to 2 times u plus p transpose lambda. Set that equal to 0. Then I find the derivative of JA with respect to lambda, vector lambda. That's pu minus fg. Set that equal to 0. I get two equations here. I get 8 equations here. So I have 10 equations and I have 10 unknowns. Right? I have u, that's an unknown, that's an 8 by 1. Lambda, which is a 2 by 1, is unknown. So I get 10 equations and 10 unknowns, and I solve for that. Okay, so we had a vector constraint, we had a scalar cost, and we put them together using a vector Lagrange multiplier. Any questions? Yeah.
How do you get Lagrangian dual equation from original equation?
You mean the augmented equation? Well, which equation?
The dual, Lagrangian dual, like where you first try to minimize. It came up for the like SBM lecture.
I have to see specifically what you mean. I don't know the dual equation. Sorry. Maybe you can write it down for me so I can think about it. Do you see how we meet the constraint here, though?
Yeah.
So, that's one of the, by finding the derivative with respect to lambda, you meet the constraint. Okay. All right, guys. You have homework for today. It will help you